So hello everyone. The topic of my talk is practical learning to learn, and this is a talk about machine learning in some sense and what learning means. And I think this field in particular, this learning to learn field, we're going to talk about meta learning, is really, really interesting, and I think it's going to be one of the next big things. And we're going to talk about a very theoretical result in learning to learn. But we're also going to talk straight after about a very, very practical simplification of things, which is really useful, which means that this is a practical learning to learn talk. And this is only 30 minutes, and it's a huge topic, so really this is the brutally short introduction to practical learning to learn in a sense. So what is the talk going to be about? What is learning to learn? Well, learning I think about as like taking a data set and building a model, sort of fitting a model, so that we can use that in some sense later. And it talks really about a single data set. Learning to learn is much more about the idea that we don't have one single data set. Instead, we have lots of little, somehow related data sets. And our task is not to learn one model on this big data set. It's to learn how to learn when we get one of the new little versions of a data set. And so it's got a couple of really good pieces around it. One is that sometimes our problems are framed as these lots of little problems. And what's particularly interesting about this case is that we can use this system to learn, to have a good model on a totally new set of data we haven't seen before, where we might only have like one single example per class. So at the very end, we'll show a demo of what we call single-shot learning, where we have a machine learning algorithm that can work with one example for each class. It's a very powerful technique. So everything starts with a data set, I guess, and we're talking about supervised learning. So we're going to have this idea of, I'm going to introduce some notation bit by bit. We're going to have an X and Y. Our X is our inputs and our Y is our target. So again, this is very much in the supervised learning space. And if you've trained any a novel machine learning on large sort of problem, you don't need a data set, you need a very big data set. And this is one of the big cons of this idea of how machine learning works for neural networks in particular, that we often need these very large data sets, which is not a good thing. And why? It's because if the relationship between the X and Y is very complicated, then we need some sort of complicated neural network, whatever that means, complex in terms of architecture or complex in terms of number of parameters. And roughly, as a guide, the more complex the neural network is, inductive biases aside, the more data we need to train it. So any method that we can sort of make use of that can reuse learning across different data sets is very handy. So we're going to be talking about learning a function, f. This is our thing. F takes x and gives y. So x is our input and y is our output. And the target of our learning is really this idea about what is the f going to be. Now, F, in some ways, encapsulate this idea of a neural network, but I'm going to rephrase it a little bit, and I'm going to think about F as being like the style of neural network. So what are the layers, like, how are they connected? And I'm going to really call out explicitly the parameters in theta that I've got here as being like the weights and biases for the network. So I'm going to really explicitly talk about the theta, the parameterization of this network. And so really F takes two things. It takes them inputs, but and also what are the current weights and biases, so to speak, and has an idea about what this y should be. So I really want to call out this theta as being something special. So the optimization task, the learning task we have is, for my x and y, what is a good theta? This is the main task of supervised learning. And so the workhorse for training neural networks is a thing called gradient descent. And I'm going to go through a really simple sort of high-level version of what gradient descent is, because I need to build some building blocks about how the algorithms later work. So how does gradient descent work? There's this rough idea that we're going to start with some random value of the parameters. And then while we're not bored, we're going to go through this little loop. We're going to pick some examples. We call this a sample of x and y. This is like a little bit of the data. We're going to evaluate that function f, given this particular x, and the current set of theta we have. Now that's going to be, it gives us this y hat. It's like a predicted value. Now, because the theta is random at the start, it's going to be pretty terrible. This y hat's not going to be very good. So the next concept we have in this loop is this idea of a loss. This description, which is the line 5 here, it's the description of how good the network is currently doing. We have an idea of y, which is the true value, y hat, which is the sort of output of the network, and we have some way of quantifying what we call loss. Now, I'm not going to talk too much about what it means, but it's just really a function we have that says how good is this particular sort of output so far. And of course, at the start, the loss is going to be bad, whatever bad means. In the next step, this line 6, we have this idea. This is a fundamental idea of gradient descent, clearly, this idea of the calculation of a gradient. So we've got this upside-down triangle, that's a nabla. This is an operator we use that says, given parameters and an idea of loss, what are the gradients in double quotes. And the interpretation of what gradients are for the purpose of this talk is summarized in line 7. The gradients are a sort of reflection of how we need to update the parameters a little bit. And we actually only do it a little bit. We have this alpha in there, and we scale the parameters back a little bit, the gradients with this update. So we're going to really think about gradients in this sense of like, how do I need to change my parameters so that, if we sort of wind backwards here, I do better according to this loss function the next time I see these examples. So this is the workhorse of how we train neural networks. From line 3 to 7 here is about saying, given a little bit of data, currently we know about, and the behavior of the network, how do I bump those parameters just a little bit so that the next time I see that example, I do a little bit better. And this loop will just repeat and repeat and repeat until we're bored, and that bored condition can be all sorts of reasons why we get bored, but the end goal of this is to have a set of parameters now that for all the data we have, the loss is low. Now, I'm actually going to sort of compact this a little bit, and so we know we're already getting into notation overload, depending on how much you've done this in the past. But this line 4 is just a compact version of what we just talked about there. If I read that from right to left, we've got the idea that for a current theta value, I can evaluate it. I can evaluate this network, that's the F. I can look at how the loss goes, and I can calculate gradients, and I can bump my parameters. So that line 4, if you're not familiar with this sort of notation, I just want you to put that in your head as like a little unit of sort of code that represents the idea that we can do a little bit of learning. So this 2, 3, 4 is just this loop. We're going to get a bit of data, we're going to change our parameters, get a bit of data, change our parameters until we're bored. Now, I call this vanilla gradient descent because in actual fact, we don't normally use this directly in its form. Instead, we have what we formally call the slightly fancier version of gradient descent. And what we do in this case is that we have this slightly different version of things where we have line 6, we have an idea of what we call an optimizer. And the role of the optimizer is to take those gradients and just transform them in some way, which means that this whole method runs faster. And that can be lots of different ways that can work. Maybe it's about making things go quicker, or maybe it's about stability of training. But the main thing is that vanilla one I talked about actually is not really practically what we use most of the time. We use instead this slightly fancier one. And what goes inside that optimizer box is like a goal of research. What is the one true optimizer? No one really knows what it is yet, but we have a whole bunch of them, and over time we just have our favorite ones. And something like ADAM at the moment, which is this adaptive momentum method, is very popular for lots of people. And really we would just empirically choose one based on what gives us the most performance. So just, even though we don't use the vanilla one, and I introduce this idea of the optimizer, for the rest of the talk I will use the vanilla one just to make the notation a bit simpler, but there's no reason why we couldn't swap in a more complicated optimizer as we go. Cool. So let's think about this idea of the parameters and the change in parameters with a picture. So really, what is this optimization doing? We start off with this theta 0 down in the bottom left, and using this idea of sampling some data and bumping the gradients with the gradients, I sort of move that theta to some point I call theta star here. This is this idea about it. Somehow we've got to a point where, based on our data and our loss, the gradients don't want to change things anymore. This is convergence. We've sort of learnt a good set of parameters. And you can think about, there's a couple of interesting things here about this idea of theta 0 and theta star. Like, are they special in some way? Are they distinct? Does it matter where I start? Is it unique where I end up? There's a whole bunch of things that are interesting about this sort of relationship. And if I think about a very simple problem, so linear regression with a single variable, something very simple, simple loss, for example, we have a scenario where sometimes that theta star, the best value of the parameters, is actually globally distinct. There is one value, and it also turns out in these very simple problems that it doesn't really matter where we start. You can just sort of randomly pick any theta 0, and using this method, we will always come to this sort of common one true version of the parameters. Now, that's the simple sunny day scenario. It's almost never like this in neural networks. Well, it never is like this in neural networks. It's a lot more complicated because of the nature of the functions. And two things are fundamentally different. Firstly, the idea that the theta star, what is the best parameter for this particular set of problems, is not distinct anymore. There's a very, very large number of them. We might take a bit of data and start in a random spot and get to an equivalent version of that performance of that network, but actually be in a totally different parameter value. So there's many, many, many theta stars, which will be equally good for the way we've described our problem in terms of the data we're training on and the loss function we have. Another thing that's a little bit different about these more complicated functions is it starts to matter where you start. The theta 0s can make a big difference. Luckily for us, nowadays this sort of things are a little bit hidden away, and for the most part, the way you sort of build your network comes for free with initialization that is sensible for those structural components. So a lot of people wouldn't even think about where they start. Maybe there's some problem where you want to tune it or something, but for the most part, it doesn't matter. It comes for free with the framework. But we get it for free, but it doesn't mean we can just totally randomly start. It does sometimes make a difference. So that's a big difference with how neural networks work compared to simple stuff. And we'll carry these two ideas along with us quite a bit. So that was for one single big data set. Things are a little bit different when you have like mixes of data sets. And a really common problem we have, or a use case, is that I have available to me a very, very large data set with a very large model that's been trained by a very large internet company, but I have a new little data set that somehow is related to that data set, but it's not totally the same, and it's my data, not their data. So I have access to this big data set, I have access to a model. How am I going to reuse that model that's been trained for my task? How do I sort of accelerate things by combining stuff? If I think about the training of that big model, through this complicated optimization loop, something like this happened. They started at a theta 0 somewhere and they ended up at a theta star. So one thing I can do is to say, well, I'm going to download this model, which is effectively the theta star of someone else's training, and I'm going to use that as my starting point for my problem. So I'm not going to start randomly. I'm actually going to start from wherever they ended up and then go from there. This idea is called fine-tuning. And it works when the problem that, as you have, the problem of your X's and your Y's are close enough to somebody else's problem that it actually turns out that in terms of where you want to have a theta 0, their theta star is better. And so this can actually make optimization feasible in some cases where it wouldn't have been otherwise, because the space of all possible theta 0s is very large, but their theta star is a good place to start. This idea is called fine-tuning, and it's used sometimes, not a huge amount. But it's going to be the core sort of technique we're going to talk about more later. Another common one is to do with the nature of how this f function actually sort of represents things under the hood. So if I have this function f that takes this x and theta, this function f as a neural network is actually not just a direct mapping from x to y. It's actually made up of a whole bunch of f's, which, like the layers. So you can really think about this, f1 is taking the input and changing things to make it more like f2, which then changes things to make it look more like f3. So this could be like a 4-layer neural network. And depending on your network and what you class as a layer, there could be tens, hundreds of f's, really, that are all sort of composed together in this way. So what each of these f's is doing is it's learning a transformation of the data that is useful for the next thing in the pipeline. So f takes x, f1 takes x and just munges it a little bit, for f2, which munges it a little bit. And it's common that each of these also does a form of dimensionality reduction, that the x at the start is very high dimensional and each of them sort of does a form of compression, useful for the next ones down the road. Now, each of these f's has their own parameters. So really in that top row, that theta is made up of this theta 1, 2, 3, 4. So if my x in my problem is like the x that was in this problem that was learnt, I could maybe make the hypothesis and say, I'm going to take f1, 2, and 3, and I'm actually just going to reuse them as is. I'm going to treat them as like a hard-coded thing. That's what I'm going to call G. And I'm going to take that x and run it through these first 3 layers, and it's going to transform that x into something that is useful, some sort of features. And what I'm going to learn is just this theta 4 at the end. And the idea is that theta 4 might be very small in terms of cardinality compared to theta. Maybe theta 4 is like 100th of the parameters. And the less parameters I have to learn, the less data I need. So I can get away with a smaller x. This idea of using these representations that have been learnt before is called transfer learning. And this is something that I know Noon's going to talk a bit more about in the next talk, so that's going to be cool. Now, transfer learning, again, like we talked about with the optimizers, is a useful thing for our toolkit. And it's going to be applicable to the things I'll talk about later. But again, for simplicity, I'm only going to talk about fine-tuning. But that's not to say that the bits at the end couldn't make use of transfer learning as well. Okay, so this is the third version of the problem, and where we're actually starting to get to the idea of meta-learning now. The idea that I don't have one big data set, or one big data set and a small data set. I've got lots and lots and lots of little data sets. And they're somehow related. And by somehow related, I don't mean as simple as they're all pictures and the Y's are all the same in terms of, like maybe I'm doing classification. So say Y1 here is cat versus dog versus tree. If all the Y's are of that same form, cat versus dog versus tree, then I could just put all this data together. I could jointly train one big model by putting it together. But what I'm talking about here is where each of these Y's is actually disjoint. So maybe Y1 is trying to predict cat versus tree versus dog, and Y2 is trying to predict triangle versus square versus circle or something. So each of the Y's here is totally disjoint. and the union of them potentially, the intersection of them whole maybe is nil even. So the learning to learn problem is to say, how do I learn about all these data sets such that when I get a new data set, it's really easy and quick for me to learn a classifier on that. I want to learn how to learn in this problem space. So this is really what the meta-learning is about. And the idea that this new data set can be very small. So few-shot learning is where we might have only 1 or 2, 3 examples of each of these. But we'll talk, this method works for what this great case of single-shot learning. So we'll show a demo of this at the end where we can have a single example of each of our classes, a single triangle, a single square, and a single circle, and learn a classifier from that. So it's really good for very, very low data. Okay, so I'm going to make this last piece a bit more concrete by talking about a common data set that people use for meta-learning. It's called the OmniGlock data set. And the OmniGlock data set is made up of these pictures. You can see here, like 100 by 100 black and white pictures. And there's about 50 different alphabets. They call them scripts. So these are like character sets. Each character set has about 30 or so characters roughly. And then each character has examples drawn by about 20 humans. So we have these alphabets, 30 or so alphabets. Each alphabet has 50 alphabets, 30 or so characters per alphabet, 20 examples. So it's some large number. We can take this very large set of data and we can turn it into lots of little data by sampling across this large data set. We call these tasks. So this example here is an example I'm showing. These are three sets of XY pairs, basically. These are distinct tasks. In these cases, I'm doing 4-way classification. So each of these examples has 4 different classes, and I only have 3 examples per instance. So this is, it's 4-way classification, it's 3-shot. So I'm only getting to see 3 examples. And I've also got this one little one off to the side, which is like a bit of a held out data, like a bit of verification data. So with this very large data set, I can keep sampling lots and lots and lots of little data sets. So I don't just have one big data set, I've got lots of little ones. So this is a common thing that people use, OmniGlock, and this OmniGlock data set is what was used to train the thing I'm going to demo at the very end. So there's lots of actually different ways of thinking about this idea of learning to learn. How do we do it? Sometimes people frame it as an optimization problem. Sometimes frame it as how do we actually build our neural network. But I'm going to frame it in the parameter sense. This is the one that I think is the most practical. How do we get this learning to learn situation to work when we're talking about parameters? And really what we're looking for is we're looking for a really good theta 0 for any problem that comes in the future. If we can pick a really awesome theta 0, then we only need to make these very small number of gradient descent steps with our single examples to get to a classifier that works. So is there, for something like the OmniGlock data, a perfect theta 0, which is like in a really good spot? Because you remember the theta stars, the ones where we end up, there's lots and lots of them. So the idea is, of all those theta stars that are available, which would be the absolute best single one to pick that would generalize to a new version of this task we haven't seen before? So again, that's this idea. Many, many theta stars. Which one would be the best one for our new problem? If we had to make a choice about this idea of fine-tuning, how do we actually encapsulate this idea of fine-tuning into the learning algorithm? How do we do backpropagation across the fine-tuning step? This is the key of meta-learning in the optimization framing. So this is the fundamental algorithm for doing it, the first one I saw, and this slide is the most complicated slide I have by far. We're going to walk through it. It uses all the pieces we had so far. This comes from an ex-colleague, Kelcey. It's called model agnostic meta-learning. And the reason I really, really like it is because any model is usable in this framework. You don't have to have a particular network architecture. You can use anything. So it's going to have the same pieces we had before, and I'll walk through it again. So if you look at 6, 7, 8, this was the thing we talked about before, the gradient descent step. So we have this little loop internally that does some gradient descent. But it's actually wrapped in this case around a larger loop. You can see this line from line 3 down to line 9, where we actually do this idea of a task. So again, I'll step through the thing while we're not bored. So again, this is a loop we just keep on running forever. We're going to do this next step from 3 to 9 some number of times. This is the tasks we're basically sampling. In the OmniGlock set, maybe we do this 10 times. We're going to sample 10 new little tasks, 10 examples of sets of these characters. And each time, each one is random. These are these x1, x2, x3 examples I had before. 4 says that we sample a task. That's a tau. So this is one particular task. This is one of these sub-small learning problems. 5 says that we're going to start our parameters, our theta 0 for this particular task, is from this canonical set of the best theta we have so far. 6, 7, 8 is what we talked about before. But rather than in the last case of gradient descent, I said we do this while we're not bored. This time we're just going to do it for a few steps. So we're going to take this parameter we've got so far and for this random new task, and we're just going to do a little bit of learning. We're just going to take it a couple of steps. So this line 6, 7, 8 is about this idea of saying, for a new bit of data from this randomly sampled task, let's do the backpropagation, this gradient. So line 8 is quite a long one here. Given my theta, reading from right to left, given my theta for this particular task, when I evaluate my function and I look at my loss, how do I update those parameters? So that 8 is the classic gradient descent step we had before. And we just do that a little bit. Now we actually repeat this step many times, say 10 times for 10 tasks. So what are we doing? We've got a bit of theta. We're going to pick a random task and we're going to do a little bit of learning. And we're going to pick another little task and do a little bit of learning, and pick another little task and do a little bit of learning. Each of these tasks will move the parameters in different directions based on what was a good set of parameters for that particular task. We do that maybe 10 times. Now this last piece, line 9, we actually get a little bit more data as well from that particular task. One bit of data that the learning algorithm didn't actually see during the gradient descent steps. So at the end of that loop, from 5 to 9, we've now done 10 little independent learning sort of exercises from that data. And then the last line, in line 10, is the combination of these things. We had that canonical set of parameters we started with. We've now done this 10 sort of sets of learning. We're now going to go and actually combine those 10 together to make one single update for the theta. And so if you read this from right to left, you get the idea that, again, we had that for a particular task, 1 of 10, we're going to calculate the F. We're going to calculate the loss on this little bit of data. And what's interesting about this, and maybe we won't go too much now, is that loss on line 10 uses a little bit of held out data that actually wasn't seen during learning. And the reason for doing that is it's a form of cross-validation. It's important. And then the main crux of this, I guess, is different, is there's a summation. There's an idea that we sum those together. We had the 10 and we do sort of a summation, we put them together. And then we actually do the calculation of the gradient. So in this line 10, the nabla then is the calculation of the gradient with respect to theta. So this algorithm is very, very elegant. It's this idea that after this loop, we've now learnt a set of parameters which will do better in general on those 10 tasks, not just one task, but all 10. And so the idea is, as we do this loop again and again and again, sampling lots of different tasks from the Omni data set, we move this set of parameters into a place where it's going to be good for any now random sampling of characters you choose. So it's really directing that parameter, not just to be good on a particular task, but to be good for the purpose of fine-tuning to a task it hasn't seen yet, which is the main thing we're trying to generalize to, a new set of data we have not seen yet. Now, I called this the practical learning to learn talk because there's actually some complexities around this in terms of implementation. Line 10 in particular calculates a gradient, that nabla, the triangle, with respect to theta, but the loss is with respect to line 8, where the gradient is with respect to a different set of parameters. So what that means is you actually end up calculating a gradient of a gradient, and a lot of libraries don't provide a simple way of doing that. So often that raises some complexity in your code. And it also means that what you have to carry around in terms of trying to make this run at scale is a little bit different. Now, luckily, some very, very smart people who rolled the math out, there's a classic way of doing an approximation of this, not doing a gradient of a gradient, which is second order, but approximating it through a first order, which is this method called reptile. And this is where we get the practical side of things. This is a beautiful paper on first order meta learning. And the third author, John, here is actually the first author of PPO. So he's got 2 talks in a row now. He'll be happy. So this loop is almost the same as what we had before. We're going to start with some random parameters. We're going to, while we're not bored, we're going to sample some number of tasks and step through them. And we're going to collect again up when we started here. Where did we end up for the 10 tasks as we did this gradient descent? We're going to have a collection of them. Now, line 9 here is a lot simpler than it was before. We're not going to do another gradient calculation. We're just going to do what is effectively an average. So we started somewhere. We ended up in 10 different spots. We're just going to basically take the average update of those 10 and just apply that. So line 10 here, you can, line 9, sorry, if you read it from right to left, you can see we had some number of tasks. We're going to look at how they differ to the current. We're going to sum them up and then average them, basically. That's the sum and the divide by t. and then use that as the learning step. Now, the reason why this is, it's not as accurate in terms of the pure math behind things, but this line 9 now doesn't have a gradient with respect to a gradient, and actually now it means that it can be this step for the task piece from 3 to 8 can be run completely independently. And so we could run those in parallel. All we need to do really, the only messaging in terms of this algorithm across lines 3 to 8 to 9 is the actual parameter set. So this has a lot of relationship with things like how we normally train large neural networks across lots of machines that do asynchronous SGD, things like hog wild and stuff. The fundamental algorithm is very similar to this. It's quite amazing. So I'm going to give a demo in the last little piece of how this works, which is just literally taken. Like, I didn't make this demo. This is literally just from the OpenAI blog that describes this algorithm. And so what we've got here is 3 boxes. So this is what's happened behind the scenes is they've trained on Omniglot a system for being ready to do fine-tuning. They're doing 3-way classification in this model. So this model allows you to do 3-way classification. And it's a method of very rapid training and generalization from a single example. So under the hood here, we've got some parameters, and what I can do is I can make some new instances. So I'm going to say A, B, C, and then I'm going to draw here, and it's going to pick the A, which is not great, I guess, but it's actually usually does a bit better than that. Well, there you go. So I had to only give 1 instance for this to pick A. And the whole point of this is that this is completely, I can do whatever I like here. This method generalizes to anything based on the examples. So if I do a triangle here, that's a triangle or a square. So what this system is doing is it's put its parameters in such a point that it only needs a single example to do reasonably well in this problem. Although that one wasn't great either. That's a bit better, I guess. So this idea that I've now got a thing that only needs 1 example is called single-shot learning. So it can be quite powerful. And it all works on the basis of that idea that the parameterization of a neural network allows many, many, many theta stars, and using this idea of propagating, doing backprop through a fine-tuning process means that we can choose a theta star out of all those many potential equivalent ones, one that is in a good space for doing very rapid fine-tuning. And that is it. Thank you.